Okay, this is lecture 21. So this is on section 11.2, and we're going to talk about series. So in section 11.1, we talked about sequences, and that's just a list of numbers. And now, in order to turn it into a series, we're going to take that list of numbers and we're going to add them all up. Okay, so a series is the sum from n equals 1 to infinity of your an terms. So that means a1 plus a2 plus a3, all the way as far as you can go to infinity. Okay, so for an example, if we had the sequence of n being added up each time, then I plug in my 1 and add that to when I plug in 2 and add that to when I plug in 3. So you're taking 1 plus 2 plus 3 all the way to the end. Okay. Now, partial sums are when I stop at a certain value. We're going to call that number k. So I'm going to go say that my partial sum is going to go from n equals 1 to k of n. So we're going to go start at 1, and we're going to count up all the numbers and stop at k. All right. So if k equals 10, that means that I'm adding up the first k terms. So 1 plus 2 all the way to 10. That gives me 55 in this particular case. Okay, so partial sum just means I'm going to stop at a particular term and I'm going to add them all up. Okay, now, in general, our partial sum is written as sk equals the sum from n equals 1 to k for all k greater than or equal to 1, this forms a sequence, okay? So your partial sums, so the sum at 1 is your first term. The sum adding the first 2 is your second term. Adding the first 3 is your third term. Adding the first 4 gives you the fourth term. And that's a sequence. And we want to know if that sequence is convergent or not. So if the sequence of partial sums converges and the limit as n goes to infinity of sk is s, then the series is convergent, and s is called the sum. Okay, so sk is the sequence, and if I take the limit of that sequence, I get s, which is the sum. Okay, so s is the sum of my series when I'm adding up all the partial sums. Okay. Here are some common series. So the first one is geometric. So geometric looks like this. We talked last time about having a number to a power, and then the a in front just allows us to multiply it by something else. Okay, so it's a plus a times r plus a times r squared. Now the n minus 1 gives you the term of a all by itself. Okay, that's not always there. And they don't always start at n minus 1, so we have to be a little bit careful here. So example 2 is the sum n equals 1 to infinity of 1 over 2n. So this is geometric because this looks like some number. In particular, this is 1/2 to the n power. Okay, now if I want that to be n minus 1, I can do a little work to make that work, right? I can pull out one of them, right? So I can make this, I can make this 1/2 times 1/2 to the n minus 1, right? So now my n minus 1 works, and my a and my r, and the a and the r actually are the same thing here. So then this would be my a, and this would be my r. Okay, so it's geometric. Okay, so here's what we want to think about. We want to think about where does this go in terms of partial sums. The first thing that we notice is we know that the sequence converges, right? If I just look at 1 over 2 to the n, we know that the r is less than 1 or between -1 and +1. And so we know that this is going to converge, the sequence. But does the series, when you start adding them together, converge? Different question, okay? So in this case, we're going to use the notation that sk is our partial sums. So we want the sums from n equals 1 to k of 1 over 2 to the n. Okay, so if I write out sk, that's going to be, and I'm starting at 1, so 1/2 plus 1/4 plus 1/8 plus 1 over 16 plus all the way out to 1 over k. Okay. Now, I am then going to do something a little bit tricky. I am going to subtract 1/2 times sk. Okay. If I multiply so I'm going to multiply that partial sum by 1/2. That's going to give me 1/4 plus 1/8 plus 1 over 16 plus all the way out to 1 over, sorry, hold on, I gotta fix this. This isn't k. This would be 2 to the k. And so if I multiply that by 1/2, this is 2 to the k plus 1. Okay. Oops. They're not in line. So this would be 2 to the k. Plus I get an extra 1 over 2 to the k plus 1. Okay. Multiplying by 1/2 or by the r value shifts everything over by 1. Okay. All right. So then sk minus 1/2 sk. Think about subtracting this. Notice what happens. All of my terms that fall for between here and here. So all of these cancel out, right? You're subtracting 1/4 minus 1/4. So what I'm left with is just 1/2 plus 1 over 2 to the k plus 1. Okay, cool. Now factor out that sk. That's 1/2, right? And I'm running out of space here, so we're going to go here. So that 1 minus 1/2 is 1/2 sk equals 1/2 plus 1 over 2 to the k plus 1. And I'm going to multiply, or actually factor out 1/2 sk and take out a 1/2. That's 1 plus 1 over 2 to the k. And the 1/2s can cancel because I have 1 on each side. So that tells me that sk, my partial sum, is 1 plus 1 over 2 to the k. Okay. Now, if I take the limit as k goes to infinity of sk, that means I'm taking the limit as k goes to infinity of 1 plus 1 over 2 to the k, right? So I know what my partial sums are equal to. I can take the limit of the partial sums because that is a sequence, and that'll tell me where this goes. So when you plug in infinity here, this is 1 plus 1 over infinity, and that's just 1. Okay. So where does my sequence converge to? My sequence converges to 1, right? And the sum is equal to 1. The series is equal, the sum of the series is equal to 1. Okay. Does this work in all cases? The answer is yes for our geometric series. So in general, our Sn for a geometric series is the sum n equals 1 to infinity of a times r to the n minus 1. And again, that's a plus a times r plus a r squared all the way out to a r to the n minus 1, and then you keep going, right? Okay, so then my sk is going to be a plus ar plus ar squared plus ar cubed all the way out to ar to the k. And I'm going to do the same thing here. So I'm going to subtract r times sk. That's going to give me a to the r plus a to the r squared, ar cubed, ark plus, if I multiply ar to the k times ar, that's going to give me ar to the k plus 1. And then we subtract them. So when we subtract them, all of these middle ones cancel. And I'm left with s to the k times 1 minus r is equal to a plus a to the r to the k plus 1. If I then take sk and divide this, this is sk equal to, factor out an a, times 1 minus r. Sorry. 1 plus r to the k plus 1. And then I'm dividing by the 1 minus r from the other side. Okay. Now what happens? Well, this is a over 1 minus r plus a r to the k plus 1 over 1 minus r, right? So let's now take the limit. That's our sk. Now we want the limit as k goes to infinity of our sk. And this is a over 1 minus r plus a r to the k plus 1 over 1 minus r. And now, I need my limit in there. Okay, and now you're going to let your k go to infinity. Okay, so now what we know is that the first piece, the a over 1 minus r, a and r are just numbers, so that's fine. That's going to give you that answer, right? And this really becomes a over 1 minus r plus the limit of. Now, if you look at this piece, the k, only k is up there. So the a and the 1 minus r do not have a k in them, so I'm going to pull them out front. And this is really the limit as k goes to infinity of r to the k plus 1. And in the last section, we talked about what values of r does this converge for. So this converges to 0 if the absolute value of r is less than 1. And it diverges if the absolute value of r is greater than or equal to 1. Well, we'll just leave it off. We remember the -1 diverged, but the +1 converged. So we're not going to worry about that at the moment, though. So either this diverges, and if it does converge, then this whole second term becomes 0, and that means that your s, your sum, is the limit as k goes to infinity of sk, just turns out to be a over 1 minus r. So that's only if the absolute value of r is less than 1. Okay, so that's what we know about geometric sequences. Or sorry, geometric series. And here's that statement. So the resulting statement becomes that a to the r to the n minus 1 is convergent if the absolute value of r is less than 1. And then its sum looks like this. Now, if you're asking me, does that consistent with what we did in the example above? And that's the answer here is yes. So from example 2, we said that we had the sequence sum equals n equals 1 to infinity of 1 over 2 to the n. And I said, well, let's write this as n equals 1 to the infinity as 1/2 times 1/2 to the n minus 1, right? So that it fits our format. Then this is my a, and this is my r. So both a and r is 1/2. So r is less than 1, so that checks out. That means it converges. And it converges to s, which is a, which is 1/2, divided by 1 minus r, which is also 1/2. And that turns out to be 1/2 over 1/2, and that's 1, which is exactly what we got when we did it up above. Okay, so it is consistent with what we did up above. Okay, those are geometric series. Okay, let's take a look at this one. Here's another example. Example 3, find the sum of the geometric series. So the first thing we want to do is we want to take this Sn and write it in general. So 5 minus 10 over 3 plus 20 over 9 minus, I'm pretty sure this is supposed to be a 27. 40 over 27, because you see powers of 3 on the bottom. First thing I'm going to do is factor out a 5. So if I take out a 5, that's 1 minus 2 over 3. Plus 4 over 9 minus 8 over 27. And you can start to see the pattern here. So this is this Sn is the series n equals 1 to infinity of 5 times. Okay, so it's alternating. So I'm going with -1, but it starts out positive. So I want n plus 1 there. So it starts out positive. Then I'm multiplying by 2/3 to the n. But let's see, it starts at 0, so it's n minus 1. Okay, so that's my series. So does this fit? So that means that 5 is my a. And this that's inside, and actually we can make the -1, not that it's going to matter. We can change this so that the -1 matches. So this is -1. As well, right? If you plug in 1, minus 1 is 0, -1 to the 0 would be positive. So it starts out at the right term. Okay, so that means that my r is equal to -2 over 3. So if I want to tell whether this is convergent, so this is geometric with an r equal to negative 2/3. The absolute value of r would be the absolute value of negative 2/3, which is equal to 2/3, is in fact less than 1. So therefore it is convergent. And the sum is equal to a over 1 minus r. And so this is equal to a, which is 5, over 1 minus negative 2/3. And so this is 5 over 5/3, or 3. Okay. So that's an example of a geometric series. Another type of series that we're going to encounter in this section is a telescoping sum. Okay, so find the sum of this series. Okay, now if I start looking at terms, 1 over n times n plus 1.
I didn't get that.
Thanks, Siri. If we plug in 1, that's 1 over 1 times 2, so that's 1/2. If you plug in 2, that's 2 times 3, so that's 1/6. Plug in 4, that's 4 times 5, which is 1 over 3 times 4 is 12. 1 over 4 times 5 is 20. 1 over 5 times 6 is 30. And so on and so forth. Okay. So anytime that you see something that looks like a fraction that can be factored in the denominator, what we're going to do is we're going to break this down into its partial fractions. So let's rewrite using partial fractions. So when I have 1 over n times n plus 1, I want to make that equal to a over n plus b over n plus 1. And we've done this before. We know exactly how to do this. When you multiply everything through by n times n plus 1, you get a times n plus 1 plus b times n equals 1. You know if you plug in 0 that you get a equals 1. And if you plug in -1, you get b equals -1. So that tells me that 1 over n times n plus 1 could also be written as 1 over n minus 1 over n plus 1. Okay, so let's think about it that way. So now if we have that that series, and I take the sum of those terms, so that means I can just go in here and turn this. Put my summation notation here, n equals 1 to infinity. Then it looks like this. Then your partial sum looks like, when you plug in 1, that's 1 minus 1/2, right? So that is my for n equals 1 term. Then we're going to add on when you plug in 2. When you plug in 2, that's plus 1/2 minus 1/3. That's your n equals 2. Then you get 1/3 minus 1/4. That's your n equals 3. All the way out to 1 over k minus 1 over k plus 1, where this one is part of your n equals, these two are your n equals k term. Now take a look at what happens though. If I look at this term and this term, they cancel. This term and this term will cancel. All the way up to, prior to this one, you'll have a 1 over k sitting there, and these will cancel as well. So what happens is everything between the first and the last is going to cancel out, which means that this reduces to just sk is equal to 1, the first term, minus 1 over k plus 1, which is the last term. So this is the sequence of partial sums. So if we look at the limit of that, the limit as k goes to infinity, and I'm running out of space, so let me move this to the side. Okay.
Hello.
Sorry, I'm recording. So if I take the limit as k goes to infinity here of this sk, that's the limit as k goes to infinity of 1 minus 1 over k plus 1. And when we plug in that infinity, that becomes 1 minus 1 over infinity. This goes to 0, and I get 1. Okay, and so what happens is that this is a telescoping sum where essentially the ends, the middle all condenses, and I get the first and last term only. And if I take the limit, I can find the sum. Okay, so that's what it means to be a telescoping sum. One of our two more quick things here, the harmonic series. Okay, the harmonic series is a particular series. That's the series when you're adding n equals 1 to infinity of 1 over n. And this one always diverges. Okay, highlight this here. Harmonic series diverges all the time. Okay, we're going to be using that one regularly throughout the rest of chapter 11. Okay, I'll show you the proof in the next section. Our next theorem, if the series is convergent, then the limit as n goes to infinity of an has to be equal to 0. Okay, your sequence has to go to 0 if your limit's going to converge. If your limit is approaching some other number and you're adding up numbers that don't get smaller and smaller and smaller, there's no way that that's going to converge to something. Okay, the opposite is not true. If your limit does equal 0, that does not tell you that it's convergent. Maybe it is, maybe it's not. Okay, but the opposite of that is actually true. So if your limit does not exist or it's not 0, then your series is definitely divergent. Okay, so we can show that this one is divergent by taking a look at the limit. So if you take the limit of an as n goes to infinity, so that's the limit as n goes to infinity of 2n over 3n plus 1, that turns out to be 2/3, right? Because that's our rule when our powers are equal. And that's not equal to 0, so this one will diverge. Okay, so test for divergence is one of the quick tests that we can use to show that something's divergent. And then lastly, we get a couple of properties here. If we have two series that are convergent, if you have a constant times a convergent series, then that series is also convergent. And if you add or subtract, hold on, typo, this guy shouldn't be in there. If you're adding or subtracting two convergent series, their sum or difference is also convergent.